This conference will now be recorded.
Good morning. Good afternoon, sir.
Good afternoon, Khadi ji.
Ji, good afternoon, Chair ji.
Sanjay ji.
Yeah, good afternoon. Good afternoon. We are eager to listen you, sir.
देख लेता हूँ कि ठीक है कि नहीं। अब बताइए, ठीक है सर? बैकग्राउंड भी
What, sir?
बैकग्राउंड और
Yes.
वीडियो ठीक आ रहा है सर?
Yes,
Yeah,
sir. Yes, sir.
very nice, sir.
Clearly.
And
Okay.
today you are fresh also. Today energy with full energy post lunch.
घर बैठे सर, इससे ज्यादा और क्या कर सकते हैं?
And today you have changed the location also. I don't see that find the same place today. You had some other place.
Within one room, I normally choose two directions.
Great.
एक ये बैकग्राउंड इज नालमेरा, दूसरा एक दीवार है।
One is pre-lunch and one other is post-lunch.
एक रात को शाम को जब होती है मीटिंग 6 बजे के बाद, so that will be wall, and during the daytime it will be this background.
जर खाडीचा कार्यक्रम चालू आहे आमचा, एक थोडा वेळ बघू. 4-3:30 ला येणार जरा.
So we have 7 now. Lot of people are yet to अभी जुड़े नहीं है, जुड़ जाना चाहिए.
When everything is available at free of cost now, nobody will bother, sir.
इंडस्ट्री में से किसी को बुलाया सर आपने?
Yeah. We have invited. There are some participants from industry also.
Okay. And sir, हर बारी अलग-अलग ऑडियंस होते हैं क्या सर? First, second, third.
Correct.
So same people do not come, na?
They can come, they can join, they can enjoy, but they won't get registration certificate as well as other things.
Oh, okay. So I'll put off the video so that when the audience comes, we can begin.
Khade sir,
हाँ sir.
we'll start at 10, 2:10 sir, because
Okay, 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 sir. Okay, okay.
sir need more time, 10 minutes more also, because I requested him to add some basics. Sir.
हाँ, yes, sir. Yes.
राजेश जी जॉईन होऊ शकला तुम्ही गुड राजेश कारभारी सर योगेश सर योगेश सर काडे सर करा चालू करा
हाँ, okay, okay, sir.
जेएस सर कुठे आहेत बघा जेएस सर जेएस सर
I
please
am,
show
I
your
am,
face.
yeah.
Please show your face. We want to see you. Don't worry about participants. These are more than enough.
Yeah,
Each
yeah.
participant is yeah.
Yeah, we now have 20.
Yeah. And we'll share
As
the
soon as
recording.
as over, we'll begin. Yeah, we'll begin. Sure.
Please, sir, please. Huh? Sir,
Okay,
Khade, sir?
good afternoon. Yes, sir. Yes. Good afternoon, all of you. Today with us, Mr. J. Srinivasan Sir from Ace Enablers, Chennai. He is well known as a motor analyst in industry. In this session, he deliver a discussion on the power and power quality. He has 42 years of experience in the area of motor dimensioning, motor testing and inspection, on-site efficiency testing, and analysis of motors. Also power quality of audit, and he also involving in training and orientation programs for the industrial persons or institute persons and others. Uh, Throughout his 40 year of experience, he involved in marketing, dimensioning, and commissioning of electric motor and motor system. He has expertise in noise and vibration, thermal measurements, and their interpretation. Also, he associated with Energy Efficiency Services Limited for national motor replacement programs, FI, CCI, CII, NPC, International Copper Association, and many NGOs in the field of energy efficiency. With this brief introduction, I request Srinivasan Sir to start the session. Thank you, sir.
Thank you. Is this fine?
Yes, yes.
Yes, sir. It is visible, sir. Yes.
Yeah. Only thing is, somebody please help me. How do I remove this from the right hand side of my screen? Everything is, I don't know how to minimize it. Do you know how
Whether
to
this
minimize?
all, you want to minimize this participant list?
I think
Just
I've done
first,
that. Yeah.
first you cancel it, sir.
Yeah. I think
And
I think I have done it. Yeah. Thank you.
And there is one more. Okay, please.
Another issue I have is I can't see my own face. As long as you can see my face, I'm happy with it.
For that also, I will tell you. On top there is option view who's talking. Click there.
View who's talking. Okay.
Click there. Then you can see yourself.
Okay.
Top
I don't know. Option remote control drawing tools. I don't know where it is. View who is talking. Anyway, it's okay. I'm not very. When you record and send me the recording, I will view my face at that time. Thank you. Well, let's begin. Yeah. Good afternoon. Thank you. You people have been very patient since morning, listening to a number of speakers. I don't know with what intentions you came on board so far as this program is concerned, but we will try and fulfill certain basic needs for you as long as you are interested in knowing what's happening out there in the industry world. May I make a couple of observations? Observation number one is about me. I come from the industry. I definitely do not have any background in teaching. So my attempt here will not be to teach you. I'm not going to do teaching the teachers. So that definitely is not going to happen. I'm going to share my knowledge, my understanding, my experience in having conducted hundreds of audits in the industry, both in the electrical motor business as well as in the power quality and solutions business. Power quality and solution is fairly recent. In the last 6-7 years, I have been exposed to the power quality field. I am retained as critical power expert by a very famous multinational company, and my job is to basically do audits and then provide solutions. I'm seeing some people leaving. Are they? This is my second observation. Are they non-electrical people? Are they going to imagine that this is also going to be another electrical topic? If that is the case, my request is please stay back. I will try and make it as interesting as possible to you in general, because my observations and my contributions will be towards industry management of power and power quality. And both are important. Don't think it is beyond the purview of the mechanical or chemical industry people, because industry management per se is a collective responsibility. Electrical, mechanical, and process people, chemical process, will all be involved in this activity. And from the sense that the industry management is a collective responsibility, I would request you or plead with you to stay back and listen to me, give me an opportunity to present my case. We have been hearing this harmonics of late. In Maharashtra, for example, we now have KVAH billing. Some of you people who have done energy auditing, or people who are involved in the energy domain, or some of you from the industry may have come across this as a recommendation from the electricity board or distributing utility company, that the billing will be from now on. I think from April it will be KVAH billing. A lot of people have identified that there is a gap between KVAH and KWH. So today we will discuss in about 20 slides the basic understanding of harmonics, which are all the sources which generate the harmonic, what effect. Harmonic is like God. You cannot visualize it, but it will manifest in different forms. So in which form you are actually visualizing the harmonic and interpreting therefore the impact of harmonic can be seen by you from these 20-odd slides. You see, any device that produces a non-linear operating characteristic will produce a distorted waveform, which is what is called as harmonics. So typically, you know what is a sinusoidal shape of a waveform, AC current, alternating current. Whenever that shape is disturbed or distorted, we will call it as the effect of harmonics. So this harmonic can be grouped into basically three types of being generated by three types of equipments. So power electronic equipments like variable speed drives. Nowadays you will find the growth of variable speed drives is also as big as the growth of motors, plain motors itself. That goes on to prove that not only for new motors, also for existing motors, VFDs are chosen for energy saving. So as an energy saving opportunity available either by a mechanical engineer in terms of fans, power pumps and compressors, or in terms of the process engineers whose process requirement can be optimized by varying the speeds and optimally reducing the speeds, the energy saving is a resultant benefit apart from meeting the requirement of the process. Therefore, variable speed drives are very common. UPS again in buildings you cannot avoid using them. Rectifiers, switch mode supplies, static converters, thyristor systems, diode bridges. These are all electronic components which change the wave shape and then provide you multiple opportunities to operate the equipment or also make energy saving. Arcing equipments, for example, nowadays you find a lot of automotive industries or semiconductor industries coming up where they have this arc welding, TIG welding, MIG welding, and those are again equipments which will cause shape change, and that will be affecting the grid in terms of harmonics. And saturable devices, some of the transformers, motors, generators, they have also got their own contributions to the harmonic per se. So this is what I meant. 50 cycles are there in India, 50 hertz. So this is one cycle. So one wave shape, which is sinusoidal, in one cycle is shown like this. But if that is distorted, and if there are 5 such cycles in one cycle, 5 such waveforms in one cycle, it will be contributed by the 5th order harmonic, which is odd order. Typically, even order harmonics cancel themselves. So you will not find after the fundamental being 1, 2, 4, 6, 8, these order harmonics will be cancelled and you will not find them in any of the equipments that you use to measure the harmonics. So you will always find the odd order harmonic. So 1, 3, 5, 7, 9, 11. These are the numbers which you will typically see in a wave shape. So if there are 5 wave shapes within one cycle, it will be caused by the 5th order harmonic. If there are 7, it will be caused by the 7th order harmonic. And the standard now prescribes that you have to measure up to 50th order, 50. Right now, the standard is not talking about beyond the 50th order, but there are already some schools of thoughts on orders up to 100. So we will not bother too much about anything more than 50th order. So typically, you will find that when an equipment is using multiple orders of harmonics, all these harmonics will get superimposed. See 1, 5, 7, and even more, and they will take a shape like this. So if you use an instrument, power quality instrument, to measure harmonics, you will find that the wave shape has become like this. What was supposed to be a simple sinusoidal wave shape has become like this. So this is the impact of harmonics in the system. So how do we understand the sequence of harmonics? So if any one of you is going to discuss harmonic in any class or any industry area, we will have to understand how these harmonics are sequenced. So first order harmonic is called the fundamental harmonic. Second is even, therefore it will not be counted. Like I told you, even numbers are not counted. It is a negative sequence harmonic, but then not measured or counted. Third order harmonic is called zero number. It's called zero sequence or triplen harmonic. You will come across the name of zero sequence as triplen, TRIPLEN also. Fourth order, again, it's a positive sequence but not counted. Fifth order is negative sequence. Sixth order is again a zero because it's a multiple of 3. Seventh is positive. Eighth is negative. Ninth is again a zero sequence. So as you can see here at the bottom, as you can see here at the bottom, the positive sequence will be fundamental 4, 7, 10, and 3 plus 1 of orders will be called as positive sequence. Negative sequence will be 2, 5, 8, 11, or 3 plus 2 will be the order of sequence. Zero sequence will be 3 and multiples of 3. Typically, we will measure odd multiples of 3. That means 3 into 3, 9, 3 into 5, 15, 3 into 7, 21, 3 into 9, 27. These are all called as triplen or zero sequence harmonics. They are called as triplen or zero sequence harmonic. These are caused by single phase loads with 2 or 4 diodes. And in a typical application, all these triplen harmonics or zero sequence harmonics will club together and typically flow through the neutral. Some of you who are electrical, you will now understand why National Building Code specifically called for, instead of TPN, they called for equal size or even 2 times larger size for neutral. So you will understand, since the incidence of harmonic has increased because of the nonlinear loads, people have been using 2 times the conductor size for neutral, while RYB phases, 3 phases, are normal size. So the reason is because of the flow of unbalanced current flowing through the neutral. Now this negative sequence and positive sequence are basically, although the numbers are like this, 6 pulse drive in a 3-phase VFD will cause 5th and 7th order harmonic. It is a 6 pulse drive, but the harmonic will be caused, like I told you, manifestation of harmonic is odd numbers, not even numbers. So 5th and 7th will be shown. 5th is negative sequence, 7th will be positive sequence. So you will have to add 5 plus 6, 11, 11 plus 6, 17, 17 plus 6, 23, 23 plus 6, 29. These are called as negative sequence harmonics. They don't club together, but they will have an impact of negatively imposing a torque to the rotating machine. We will see a couple of slides are there on this topic. You will understand them when we go to them. Similarly, positive sequence will be 7, 7 plus 6, 13, 13 plus 6, 19, 19 plus 6, 25, 25 plus 6, 31, so on. So up to 50, this is how they will be numbering the positive sequence, negative sequence, and zero sequence harmonic. Each type of harmonic has got its own impact on the electrical network as well as the rotating electrical machines. I have a couple of slides. As we move forward, we'll take a look at them. So we have seen the basics of harmonics. You know what is a harmonic? Harmonic is basically a distorted waveform caused by the nonlinear loads in the industries. You need nonlinear loads because without them your industry cannot function. What are all those loads which generate harmonic? We'll take a look. For each I have only about 4 slides, so don't fear. It will be simple and you will be able to appreciate. So equipments using switched mode power supply, SMPS, like television, computers, and other IT loads are generators of harmonics, particularly third order harmonic because they are single phase loads. Equipment using power electronic devices like AC, DC drives, frequency converters like VFD, like I told you, rectifiers, arc and induction furnaces, UPS, compact fluorescent and other discharge lamps. All these are generators of harmonics. All these in different shapes generate harmonics, different order of harmonics, and as we go, we will understand what these are. So, like I mentioned to you, all PCs which you use, your laptop or your PC at home or a smart TV, it almost 100% of its current is harmonic current. Thankfully, the legislation that we have, KVAH billing or penalty for harmonics, as in Tamil Nadu, they don't address the household, equipment. If they address, we will not be able to use any one of them. See, if the current is the current is just full load current is 2.4 ampere, almost entire 2.4 ampere is a harmonic current. If you take harmonic as a bad word, then it's called bad current. And this is the total harmonic distortion current, 93%. And when you split it into 3, 5, 7, and so on, you will find out of 93, 78 is third order, 44 is fifth order, 17 is seventh order, and so on. So all orders of harmonics actually are harmful to your grid, to your network system. And these are caused because of the rectifier circuits. So this is the problem with the harmonic. Your PC, whatever you see at home, electrical gadgets like your TV, they are all causing heavy harmonics to the network. This is by a CFL. Now we have gone to LED. LED also has harmonics if you don't buy from the right source. So again, you see 1.7 ampere is the current, but almost 37% of it is a bad current or harmonic current. So this is caused by the CFL. Then the variable speed drives, you will find 2.8 ampere single phase, 2.8 ampere, 124% of single phase variable speed drives are harmonic currents, 81 in the fifth order, 74 in the seventh order, and so on. So this is a danger of using all these nonlinear loads because they cause harmonic distortion in current as well as in voltage, which are undesirable. So we need to address them for solving the problem. So what are the effects? I am not discussing the solutions. This particular presentation is almost 120 slides. I carefully chose first 20 slides and removed a few of them because they were not going to be very useful to you for this particular class. Dr. Court asked me to prepare a basic presentation slide. So I have taken 20 slides approximately here. So we'll see what is the effect. Why is it important that we have to address the generation of harmonic and how we see the effect of harmonic. See, if you see the core of a cable, and if you were to touch the cable, you will find that the cable is very hot because the harmonic current will flow through the periphery of a cable. The core of the cable will not carry the current, so it will not be hot. But then the periphery will be very hot. So any load which is carried by a nonlinear load which is carried by a cable, invariably you will find that the core is cold, the periphery of the cable is hot. I will take a few minutes to explain this phenomena so that you will be able to appreciate this. When we put a DC current on a conductor, the DC current will go from one end to another end, from positive to negative, and the current will flow across the entire cross section of the conductor. You can visualize from the animation here. So it will flow across the entire cross section of the conductor. Whereas when you use a 50 hertz AC current, the current will not flow to the entire length of the entire width of the or cross section of the conductor, but rather it will be flowing towards the outer periphery. This is for a 50 hertz current. Take a look at the 250 hertz current, which is basically harmonic current, fifth order harmonic, because 5 into 50 integer, multiple integer of the harmonic. So 250 hertz current will flow only at the periphery, and this is the reason why you will have what is known as the skin effect. The skin effect will cause heating of the outer sheath or outer conductor of the cable or bus bar. So you might find, if you go to an industry, you might find some sheath which is provided on top of the, or a cover which is provided on top of the bus bar would have melted and flown. That's a sure indication of harmonic flowing in the bus duct. Similarly, the bus ducts will get loosened up at the joints, and that will create a vibration, and therefore there will be a huge noise, humming noise. These are indications of harmonics. Even when you do a walkthrough in the electrical panel room, from the transformer to the transformer to the main panel, if the bus duct has been used, and if there is harmonic in the network which is going towards the grid, you will find that there will be humming and there will be heating telltale signs in the panels. Now, this is one, like I told you, the humming and the heat are one way by which you will know the presence of harmonic. The other way in which you will know the presence of harmonic is by looking at the positive and negative sequence. When you use a nonlinear VFD, the motor will have additional, apart from its own torque, it will have additional torque added by positive sequence and negative torque added by the negative sequence, which is the fifth order. 5, like I told you, 5 plus 6, 11, 11 plus 6, 17. Those numbers will be opposing the torque of the motor. So there will be reduction in speed of the motor because there is an opposition and there is also a positive torque added. It will create a pulse effect in the motor shaft, and therefore the motor will be drawing more power in order to deliver the load. Some of you who must have listened to me the previous 2 occasions, I would have repeatedly used the word that motors deliver what the load demands. So when the whole time job of a motor is to deliver what is demanded by the load, then the motor will make additional efforts, take more power to deliver and meet the demand from the load. Therefore, the motor will run very, very hot. So this is another way to find out how the harmonic is affecting your rotating electrical system. And I'm also in a couple of slides discussing about the effect of harmonics on capacitors, primarily because of resonance. Now, when you have a nonlinear load, harmonic is generated from the nonlinear load and it is spreading to the parallel branch. So it's going from this is a load which is generating harmonic. This is a normal motor, and this is a heating circuit, and there is a capacitor in the same branch. You find that the harmonic is not only going towards the grid, it is also spreading to the other branch circuits. This is a normal habit of a harmonic. It will spread. Now, because you have a capacitor in the network without any resistance or a reactor in the circuit, the harmonic will get amplified because of the plain capacitor, and that will also flow through the grid. This is the problem of using a plain capacitor in a network which has a high incidence of harmonic. So what do? We take a look at, this is only to explain to you, on a 2500 kVA transformer, all incomer capacitors were switched on to find that 24.4% is the harmonic current. So when we switched off all the capacitors, without the capacitors, the harmonic content came down to 8.6%. So this is what we are trying to mean in the previous slide. When a plain capacitor is there in a network with harmonic generated, the harmonic will get amplified due to resonance. This can be seen in this particular graph. So you have the network impedance and also you have the capacitance of the capacitor. And these two will superimpose and amplify at this level due to parallel resonance. And this is what is causing the amplification of harmonic also. So this understanding is very critical upfront when you go to the industry site or when you handle a site. If you know there are plain capacitors and also many nonlinear loads, those plain capacitors are going to cause incremental in harmonic content, which will go to the grid and also affect your, in Tamil Nadu, it is a penalty when you exceed the limits, and in states like Maharashtra now, and most of the North Indian states, like for example, Delhi, UP, Haryana, Punjab, Rajasthan, Himachal Pradesh, and down south you will find Telangana and Andhra Pradesh have already implemented kVAH billing, which is affected by both power factor as well as by the harmonic. So harmonic in that sense is an undesirable element. It will increase your power bill and it will give you losses in the system. So what do we do? A solution for this will be to provide a reactor upstream of the capacitor. So the supply will go via the reactor to the capacitor. When you do that, there is no harmonic amplification from the capacitor circuit. So that is avoided. Whatever was originally going will go to the network or grid towards the transformer and into the grid. So this has to be understood. So that is the last slide I had. So this is a simple understanding on harmonic. Dr. Court, will you please unmute and tell me if this is sufficient? Because obviously today's program is not covering this, but for the understanding of the audience, I would imagine this would have been sufficient.
This much is suffice. This much is great, so suffice.
Thank you. Yeah, thank you. So we looked at what is harmonic, we looked at what generates harmonic, and we looked at what are the causes or manifestation of harmonic, how harmonic shows itself up in the system and network to our knowledge. As you can see here at the bottom, 21 slides. I kept my promise. Sir, I will now disconnect and go to my main program.
Correct.
Oh,
Correct.
Yeah. I will start that slide.
Correct.
Is it okay now? It's fine.
Exact.
Can you see the slides?
Yeah. I can see it is exactly as desired.
Right. So now, how many are left in the network? How many have left? How many have arrived? And what is the number now?
Number is good actually. It is 30.
30. Very good. Excellent. Thank you. Again, I am known for preparing my audience for what to expect and what not to expect. So in that sense, there are approximately 48 slides. If you remove this one slide and my last slide where I speak about myself or I speak about my connections, there are 46 slides. I will go through breezily. I hope I will make impact on you. I will create the necessary understanding of the topic. What I have actually done is I have taken one case largely of an audit we carried out in a hospital to explain all the parameters. That will be important for your understanding. Either as an energy auditor or as a system solution provider or as a faculty, electrical or otherwise. I've already made the offer to you, request to you to stay back and listen to what is this PQ audit all about. So we'll proceed with the there are also a few slides to put you in the picture. Like I always tell Dr. Sanjay Kaur when I talk to him privately, I tell him that I always use a funneling effect. Look at the overall perspective and let it come down to the topic on which we are going to have discussions. So as you can see here, India has an unenviable task of having to meet greenhouse gas emission. We have signed the Paris Agreement after the Kyoto Protocol. So India has reaffirmed their commitment to meet that target, which is 33 to 35% reduction over the 2005 level of greenhouse gas emission in our country. Very, very tough. You all know during President Trump's period, the USA cried out of this target. They said, we will not meet this target. Most of the European countries are struggling. China is way behind this target of 60 to 65%. India is not only meeting, it is also committed to meeting many times. So as you can see here, India's target can be met through adopting energy efficiency techniques. I don't know how many of you listened to Mr. Anil Chaudhary in the morning. If Bureau of Energy Efficiency is founded for the principles of energy efficiency, for the policies of energy efficiency in our country under the Ministry of Power, in the same token, EESL, Energy Efficiency Services Limited, the Asia's largest ESCO company, is also founded for implementing those policies. So you have a policy making framework and you have an implementing agency. These are unique in India. In the growing India, this important policy which will drive and the EESL ESCO model which will drive the implementation are very, very important. So if you notice here, for the greenhouse gas abatement between 2010 to 2035, there is an agency which has identified that 51% of the potential can be met through enhancing energy efficiency. So now you will connect why we are talking about energy efficiency in our country in such a level. Followed by 32% through renewables. The reason, couple of slides I will explain to you. You can take a look. The reason is India's growth is something which cannot be reversed. India is the youngest country in the world with an average age of less than 24. The average age of Europe is 40 and the average age of Japan is 47. So those two are aging societies. Whereas in our country, people between 16 to 30 are almost 68%. So I'm saying average age is 24, but between 16 and 30, the people with maximum aspirations, dreams, desire to do well and live a better life are growing, and we are a very, very young nation. So we were agriculture based when we got our independence in 1947, and at that time only 1,362 megawatt was the generating capacity in our country. Very, very poor. I'm sure you'll be able to appreciate if I give you two more informations. But before that, let's look at an industrialized India. India's industrialized India in 2021 has generated 3,82,000 megawatt. That means almost all the capacities have been built in the last 70 years time. This is a figure as of 31/3/2021. And we are an industrialist nation. And from here, our aspiration is to become urbanized nation. That means almost 80% of our population will either live in urban India by 2030 or eke out a living out of urban population, right? So at that time, the estimated power generation capacity required for our country is almost twofold or slightly more than twofold, 8,17,000 megawatt. This is projected by the CEA, and this is based on a particular GDP level of growth. So this is something which cannot be reversed. Most of our youngsters would like to educate themselves, engineering or otherwise, move to the cities and eke out a living. There is also a study by McKinsey which says by 2030 we will have 16 metro cities. Today, including Bangalore, we have 5 metro cities. 16 metro cities. Chennai's power capacity requirement during summer months like this is around 2,500 megawatt. 1947 would not have been enough to meet Chennai because more than 2 times will be requirement of Chennai. The requirement of NCR, National Capital Region, which includes Delhi and small satellite cities like Ghaziabad, Faridabad, Gurgaon, and so on and so forth, is 11,000 megawatt. and it is growing. Delhi's population is 3 crore. It's growing. Pune is growing. Baroda is growing. You know, almost all companies are exploding with population because people are becoming urbanized. So that growth cannot be reversed. And there is another outlook by another agency. This is CE again, a draft national electricity plan, which says that by 2027, we would have grown substantially beyond, this is almost 650 megawatt, 650,000 megawatt. And our growth through coal, this gray color bar, the growth through coal will have to be stopped. It cannot be allowed to grow further. Already, as you can see here, almost 62% of our power generation comes from coal-based thermal power stations. And we cannot allow them to happen if we want to meet our greenhouse gas emission limits. And therefore, new and additional renewable power sources will have to increase to 275, and they have to grow outsmart. They have to grow more than our coal-based stations. The reason is, worldwide, many countries are having degrowth or reverse growth in coal-based thermal power stations. European Union will grow in the negative. United States will grow in the negative. China also will stop some of their thermal power stations and grow non-linear loads. Only in India, this is for the year 2013 to 2040, India will continue to depend on coal-based thermal power station, and with this kind of scenario, we will not be able to meet the greenhouse gas emission norms. Do whatever we can, we will not be able to reverse this trend. So therefore, it is very important that we work on this slide where we say that energy efficiency as well as adopting new and renewable energy is managed by our country. So our country had a plan to put 100 megawatt of renewable energy under solar, 60 megawatt wind. This 100 has already been reached. This was, I think, in 2017, target up to 2022, but we have already reached this 100. So we have now revised this target. We are going up further. And if you recollect this, we need to build 275,000 megawatt renewable energy, mostly from solar. And we have this abundantly, we should do this. So that is the reason why energy efficiency will become very, very important in our country. And with this slide, I would like to pitch in for everybody involved here to be serious about it. Don't say I am not involved, I am not concerned. Whether you are at home and if you are putting off lights, fans where it is not used, you are conserving energy, and that is the foundation of the pyramid. On that, you will build energy efficiency technologies. You will go for newer, less loss-making equipments and designs, and you will also adopt renewable energy. So energy pyramid in our country will be on a broad-based energy conservation. Don't stop switching off where you don't require, converting, diverting, or completely switching off where it is not required. Buy only high efficiency equipments like 3-star, 4-star ACs or fans and so on and so forth, and also build renewable energy dependency rather than on coal and other thermal energies. So with this, we'll venture into the topic that we have taken for today. This topic I have divided into two main parts. What is the energy accounting that will help you understand, from where you will go where. So that's very important in industries or even at home. You'll be able to do this, or commercial buildings or office buildings and so on. So let's look at energy accounting. I'm sure there are only about 2-3 slides, not more than that, easy for you to understand. But let me make a commentary here. So you need to basically create a benchmark where you are. So here we are. From here, where we will go has to be decided. So the benchmark will help you, whether you are from the industry or as an energy auditing professional. You will make a benchmark, and based on the benchmark, you will identify whether you are above the average or you are below the average. Even if you are below the average, you should continue to aspire, because like they say, in a race, running race, for example, to retain the same position, you have to keep running. You can't say I have taken over all the 10 people are running a race, you are running number 1. Number 2 is trying to catch up with you, and you can't say, I can now stop because I have reached position number 1. You cannot stop. So in a race, to retain the position, you have to keep running. Therefore, when you have got a benchmark, identify where you are, you have to set a target to decide where you should be or where you want to be. Your desire has to be clearly understood. And after reaching that target, you have to exceed that target. So that is very important. Therefore, first by energy accounting where you are. So energy bill is a good tool for you to apply your mind and thoughts and understanding on what is actually happening with your industry with respect to the energy usage. So optimizing the KVA demand in a power bill is the topmost priority. I have a slide with which I will explain this better to you. KVA is called contract demand. You pay a fixed sum. For example, in Tamil Nadu, we pay 350 rupees. I don't know exactly what is it in Maharashtra, maybe 275 or 300. So different states have fixed different contracting demand charges. And you will also have charges for kWh or energy which you are using. So that is per unit, say 6 rupees 75 paisa or 7 rupees and so on. And you also pay for reactive power which you have not used but wasted towards creating magnetic flux in your operating equipments. So that is called as power factor or kVAR. 434 rupees. I'm seeing somebody putting it in the chat box. In Maharashtra, it is 434. That's a lot of money. So you need to control the kVA. When I explain in the slide, you will be able to appreciate why I'm saying this. Improving power factor and going close to 0.999 or unity will be desirable. And introducing all kinds of energy efficiency measures and techniques to reduce the kWh consumption is also important. And the clue for that will come from the energy bill. I have taken one energy bill. This is not an industry, but I think I will be able to tell you so that you will appreciate this. This is in Tamil Nadu, Anjetco. This is a railway ticket booking complex. I don't know how many of you have come to Chennai. If you have come to Chennai, and Chennai Central is the biggest railway station which connects with most part of the country, you will find a very tall 12-story building next to it, to the Chennai Central, which is a historical building. And this 12-story building has a power bill like this. Normally, I do not mention the name of the customer, but here, since it is public sector and nobody will actually find fault with me, this was done in 2013, as you can see here. The permitted demand for this facility was 2,100 kVA at that time. Right? They have not reached this 2,100. They have reached less than 90%, but minimum payable is 90%. So 2,100 multiplied by 0.9 will give rise to 1890 kVA. So they are paying for 1890 at the rate of 300 at that time. Now it is 350 in Tamil Nadu. So 1890 multiplied by 300, they are paying 5,67,000 rupees fixed in the power bill towards the maximum demand, towards the contract demand. Now let's go to the next slide and come back again. So this is 90%. If you come back again, if you come to this slide, you will notice that actual demand reached is 1764 only. See here, the kVA demand reached is 1764, which is 84%. Now they are still paying 90. So anything more than 90, they will pay actual. If it is 91, 92, 93 or 95%, they will pay actual. But anything below 90, they will have to pay minimum 90% of the contract demand. So this is one factor. Is it possible for them to surrender demand such that they do not, they bring this 1764, below 100 or above 90? So that is the expectation. This is the expectation from the bill. This is one. And there was no power factor incentive even at that time. You can find zero here. Today also there is no power factor incentive, but penalty is there for power factor, both lagging power factor as well as leading power factor. I'm sure Maharashtra also has lagging power factor and leading power factor. Both will be penalized. Penalty will be levied by the electricity bill. And total energy charges are, as you can see here, approximately 6,84,000 units, and it is being at that time paid on this basis. 7 rupees per unit during normal time, 1 rupee 40 paisa during the peak hour time, differential tariff, 5% rebate during the night hours. So this is the power bill, what it reveals. So as you can see here, optimum reduction of KVA, surrender some KVA where it is not required will be very important. Another factor that I have tried to bring out in this slide is this information. The 6,84,000 units, when you divide by 30 into 24, see 30 days and 24 hours, you will get only 950 KVA. 950 kVA divided by average power factor of 0.96, which is mentioned here in this bill, will give rise to 950 units divided by 0.96 will give rise to 990 kVA. So why 1764 when 990 is the average kVA? This happens whenever you switch on heavy starting equipment or sudden peak in demand. Between shifts, you will find this happening. So even that can be disciplined by this customer. So the idea of providing this information is to reduce 1764, also reduce 2000, what was that number, 2100 kVA, so that you will be able to reduce fixed cost. So this is what is energy accounting largely about. There are many people who have such kind of information already worked out, and this is one of our experience which I am sharing with you. I have a slide here which basically, I think this is from TERI, the Electrical Research Institute. It talks about what is a point of common coupling. Point of common coupling is basically EB power supply and the trivector meter of the industry. Where they meet, that point is called as the point of common coupling. So we will be seeing the use of point of common coupling also in the few slides that are following. You will have to understand and visualize where it is. It is not the transformer's primary. It is not the transformer secondary, or it is not anywhere inside the network. It is exactly at the point where the EB power supply and the trivector meter provided for that facility where they meet. That is where vacuum circuit breaker, that is where the point of common coupling is. And the distribution losses and transformer losses are given here as a number. These are some suggestions. The transformer efficiency, it's a high efficient equipment, could be between 98% to 99.5%. Depending on the load factor, this efficiency could be closer to the nameplate. I have a slide. When we look at that, you will appreciate that. The distribution losses are between 1 to 6%. These are in the cables, in the bus bar, and in the switch gear, or even for that matter in the capacitors. So the distribution losses are estimated to be 1 to 6%. If you are making a 6% loss or more than 6% loss, idea is to bring down this to around 4%, 3%. You can't bring it to 1%, but 4% is always a middle of the road figure, and it will help you to achieve. If there are 1 lakh units consumed in a day, 4% reduction or 2% reduction will be 2,000 units. 4% reduction will be 4,000 units. Substantial optimization and opportunity available for reducing your losses. Similarly, if you look at the end use products, motor being almost 70% or more than 70% in some industries, efficiency could be varying between 85 to 96%. This variation is primarily because of the size of the motors. All lower size motors are very inefficient. All medium and large size motors are sufficiently higher efficiency of 90 to 96%. But motors below 10 horsepower or 7.5 kilowatt are 85 or less than 85. So we need to understand how this can be deployed profitably by reducing their losses and improving their energy efficiency as a system. Last two programs that I offered under STTP here, program 1 and program 2, were about motor and motor systems, including VFD. But this time, Dr. Court requested me to provide some insight into power and power quality measurement, and therefore I chose this topic and the slides. I have certain clues here for people who are interested in addressing the installed distribution losses and operating losses. You saw this slide. Installed distribution losses are here. The operating losses are in the motor system largely. So how do we broadly look at the opportunity available for saving? The installed distribution system, like I already said, it comprises of transformer, bus bar, cable, switches, fuses, contactors, relays, capacitors, and so on. Even UPS is a part of the installed distribution system. The operating electromechanical system is largely motors, gears, heaters, and lighting, and some IT loads also. Now, what are the choices available for energy saving broadly? In the installed system, the losses are I square R losses or copper losses. Now, we can't change the profile of I. If you have to change the profile of I, you have to ask your manufacturing manager to reduce the manufacturing capacity, which you can't do. You will become unpopular. So what you can do is you can always reduce the R. How do you reduce R? Resistance is by upsizing the conductors. So a simple rule of thumb or a simple suggestion for installed system to reduce I square R losses is to upsize the conductors or increase the number of runs. I have one slide on this, not more, but I will try and bring out that information. The operating electromechanical system has losses in both copper and iron, typically in motors. And as per theory, the losses of copper and iron, when they meet, the best efficiency occurs, electromechanical system. And therefore, you must remain as close as possible to the optimum level, and therefore optimize is a solution available to reduce your copper and iron losses. Simple rule of thumb, nothing difficult to understand, fret about. Okay, now let's look at the transformer. The transformer efficiency figure will look like this. The maximum efficiency, peak efficiency will be approximately at 40% load, oil cold transformer. Dry type transformers, this morning the gentleman talked about dry type transformer also. The efficiency will be approximately at 24%, 25%. So it will be even less than that. So the best efficiency will be approximately at 40% for oil cooled. Above that, the efficiency will keep dropping. So it is not desirable to load the transformer close to its nameplate. You should optimize. If not at 40, you should restrict it to between 50 to 60. So that after that, the effect is not felt. So this is one clue. Like I already mentioned to you, you have iron losses, which is called fixed losses. You have winding losses or copper losses, which are variable losses. Where they meet at approximately 50% load, the best efficiency will occur. But typically in a designed transformer, 40% oil cooled will be the best efficiency. So I'm trying to bring out this thought in you so that you do not allow, whenever you see a transformer being loaded closer to the nameplate, 100, or some people even load it beyond 100, please caution them that they are losing heavily. I'm not discussing what kind of losses. If you're interested, you would write to us. We can share some case studies. Now I've taken, like I told you, to discuss, just give me 1 minute break, please. To discuss various topics that we discussed, that we mentioned earlier, I have taken one case study and interchangeably put in front of you various activities that is happening. This is not the entire SLD, but it's just a portion of the SLD, just to bring out the information that this hospital, which is receiving power from 11 kV grid, is using a 1250 kVA transformer, right? So in this SLD, we have also provided to the customer what is the harmonic level, both in current and voltage at this level. This meets with the standard, and therefore at the point of common coupling, this customer need not worry too much about reducing the harmonics, right? Now on the secondary side of the transformer, the harmonics are like this, with capacitor, without capacitor. So typically when we do an analysis or audit, we connect a power analyzer for 24 hours and capture 24 hours data. You will find them coming when I scroll down. Some of the slides I'll explain to you. We take the 24-hour data and multiple values and multiple solutions are discussed. So we'll go forward and take a look. This is a 24-hour data of kilowatt. You can see here on 29/7/2019, 6:45 p.m. this was started recording and ended at the same time on the next day. Right? This window therefore is 24 hours window, and this is capturing data. This is capturing data of active power kilowatt. What I have done is the cursor is where this red is there. No, this cursor is where I keep it. So cursor has got minimum, average, and maximum. And the entire window, 24 hours window, has minimum, average, and maximum. We'll take the average. We'll ignore the minimum and maximum. So the average load for that particular day in the hospital was 283.5 kilowatt. Remember 1250 kVA transformer. So only 283, less than 28, 25% or even less than 25% is the load factor. So this is probably they have purchased this transformer for future expansions and things like that. Oil cooled transformer, I know it for a fact. So what does it give to us, this information? Based on this, and this is only 23% load factor, as you can see here. Based on this Excel calculation, we can find out what is the efficiency of the transformer. The efficiency of this transformer at 100% load, fully loaded transformer, will have 12 kilowatt losses. 1250 is the output. Input would be 1262 based on the losses. So therefore, we will have 12 kilowatt loss, and the 12 kilowatt loss would have given rise to an efficiency of 99.05%. Whereas when you operate this transformer at 23% load factor, the losses would have reduced so much. From 10,750, the variable losses would have reduced so much such that the same at 23% load factor will give rise to 99.37 as efficiency. So at partial load, as you already noticed from the graph, the efficiency of this transformer is much higher. This industry can continue to expand, put additional wards and rooms and facilities till they reach around 50 to 60% of the load factor, and their efficiency will be almost 99.3 to 99.37%. We also have another format with which we calculate all-day transformer efficiency. This is very important. Any facility you go for auditing, if you take a 24-hour data and also use this format to arrive at the all-day efficiency, you can notice here, based on the data that is available, the all-day efficiency is 99.35. This is with one instantaneous value where we found 23%. This is a dynamic value where the average load factor was 22. This is fine-tuned, 22.88. The average power factor for the day was 0.982, and the all-day efficiency of the transformer is 99.35%. I do not know if anybody else is doing this exercise when they are doing audit, but we definitely do this, and we take pride in telling you that we are one of the leading exponents in the country to use this format for measuring the all-day efficiency of the transformer. Just one word of commentary. This transformer is as per IS 2026. This also was covered in the morning. If we now convert this transformer to IS 1180 level 2, then the value of energy saving will be even higher. The losses will be much lower. This 12 kilowatt loss would be approximately 9 kilowatts. So you will have 3 kilowatt unit saving per hour available to the industry, to the hospital. So same hospital, same 24-hour recording, but different parameters. We are looking at the power factor. So you will have power factor in R, Y, B phase, and also the total. PFT is total, which is the sum of the three. So the average power factor is 0.992, but you will find that in the R phase, the power factor is 0.967. So we'll have to find out why in one phase the power factor is lower when compared to the other two phases. So normally what happens is many industries and facilities connect single phase loads indiscriminately. So they may have connected a lot of single phase loads to the R phase only, because it must be the first phase that is available, easily accessible in the panels. So at various levels in the panels, single phase loads would have been added. We have advised them to take a look at overall facility and redistribute in such a way that the average power factor is not unbalanced like this. This unbalance will lead to unbalance in current, and therefore the suggestion. Right, another window, same 24-hour measurement. We are looking at the demand. See, if you look at the demand, the average demand was only 288.7, because we saw average power was also 285 or something like that. The power factor was 0.982. But then there is a peak demand which is captured as Windows maximum, which is 532 kVA. So for a 288 average kVA used, they are paying 532.3 kVA. That means 240 kVA in excess, and that is about 84,000 rupees per annum. So 240 kVA, the difference between the two, and it is showing 84,000 rupees as money available if they discipline the starting of equipments, reducing the incidence of peaking of kVA. For example, here at this is at 1445. Some maybe the AC air conditioning chiller must have been started, and that is the reason why a peak has been registered in the kVA. So this graph will help you to understand. So this is in the morning, when as soon as they come, they must have started some activities. So 500 kVA is registered in the meter as the peak kVA. And in the afternoon, when the chiller loads are started, this is a child trust hospital. So children in the morning hours will be generally comfortable. Afternoon, after the sun becomes hot, they will be starting the chiller, and therefore this must have happened. So if they find a solution to start the chiller with a soft starter or a VFD, this peaky will not register. This peaky is what causing them approximately 84,000 rupees loss. So this information is coming out of this particular one-day recording. Please remember, I'm continuously using the same one-day recording for different values and with different perceptions and interpretations. So I asked them why this peak has happened. The chiller was started at 7:15 a.m. on start delta, registering a surge in kVA. Similarly, in the afternoon, again the chiller is the largest load. So they admitted that this is the reason why it has happened. I mentioned to you about the distribution losses, or losses in the network. This formula, I'm sure this slide, when I complete this program, will be shared with already shared with Dr. Sanjay Kote. He will share it with you. No reservations, you can use them. Use this formula in an Excel sheet, or if any one of you want the Excel sheet itself for calculations, please don't feel any reservation in asking me to share it with you. I will share it with you. With this, you can be able to calculate the losses in the network, in the cable system. Apart from selecting cables for the voltage drop, short circuit current, and things like that, you can also make selection of cables for the losses in the network. So I will explain through one slide here. This is an industry, textile, where typically upsize is practiced by all the leading electrical engineers. They will not choose anything less than 300 or 400 square mm. But this one particular industry did not probably have the wisdom of the same experience. So they chose 3 runs, 2 runs of 185 square mm mostly. And the losses, based on the formula which I mentioned to you, is the resistance can be taken from the catalog. We worked out and found that the losses are like this. And if we suggested change in cable sizes, the reduction losses are like this. So almost 50% reduction is available in the network by choosing cables of larger size. Now, this could be useful for many industries which are putting up newly. For existing industry, when you make a suggestion, you have to include other 2 parameters. What is the voltage drop? What is the power factor? What is the short circuit current? And the losses. So when you do an audit, if all the 4 parameters can be taken, clubbed together and the benefit is shown to the customer, I'm sure we will be able to persuade the customer to replace some of the cables. The average cable life is about 20 to 25 years, but sometimes based on the payback, it is possible for us to educate and persuade the customer to replace some of the undersized cables. One slide, I think, on the thermography. This is an important tool which is now added to most of the energy auditing people's repertoire. The reason is that we will be able to, normally when you see, you will not see the difference in temperature. As you can see here, through the thermal vision, we found out that, the average current of the three phases put together was only 36 degrees centigrade. Whereas one phase, which is I think the blue phase or yellow phase, showed 80 degree. This is possibly because of loose connection or because of not using a bimetal washer. So we'll have to find out why it is happening and then immediately rectify before it becomes dangerous. So the deviation is pointed out in this report and the customer was asked to immediately attend to this problem. So a thermography camera can help you visualize anomalies very easily, persuade customer to undertake depending on the urgency, shutdown and rectification, or postpone, wait for the opportunity for the shutdown, and at that time carry out the the suggestions and repair. It's very important. A few minutes, you will be, whenever I see letters, I get stuck. I think most of you will also get stuck. Up to now, you must have observed that I have been using a lot of pictures, images, and filling with my voice so that you will only focus on areas where I wanted you to focus. If you want to read the slide later on, there will be ample time. But when I'm taking you through a session, my ideal approach would be to guide you to visualize only those which I wanted to visualize. This is a slide, of course, used by Dr. Vikram Singh, the then director of CEA, Central Electricity Authority. I have not taken any permission, but I have borrowed it from his presentation and used it here. Primarily, the objective was to tell you that there is an amendment made by CEA in 2019. This must have been implemented in most of the states in 2020. 6 February 2020 was the time given for implementing this amendment. CEA is the authority for electrical safety and electrical distribution in our country, as most of you might know. So in this amendment, which was issued on 6 February 2019, they specifically talked about IEEE 519 2014 being the standard. The IEEE 519 1992 was the first time the standard came in the world for harmonics and power quality. The amendment, first amendment to that standard came in 2014. It had taken such a long time. Why? We are not going to discuss, but you can pursue and find out why and what was the actual reason for it. The second thing is, in the amendment, CA also spoke about measuring and measuring methods, measuring meter and measuring methods as prescribed under IEC 61000-4-30 Class A. They have carefully omitted edition 3, which is the latest edition. And even if they have omitted edition 3, as per the standard, edition 2 is null and void. Those of you who will be interested in pursuing this particular topic can ask me to share more information with you. IEEE 519 2014 standards, how is it different from 1992? We are not discussing all that here. Time is not enough, and I'm not going to definitely bore you with that detail. So the second thing is, as per CA regulation, the metering and the method of measurement are discussed as per IEC 61000-4-30 Class A. Similarly, they are also talking about providing a power quality meter permanently installed for measuring harmonic as well as various power quality topics. So we are going to only discuss that. Why is it important that this amendment is understood and the industries or energy auditing fraternity become aware of what is happening in the domain? So this is the topic 1, topic 2, and topic 3. So from this regulation amendment, which came in 2019, this year it is getting implemented. I think the draft regulation in Tamil Nadu has also been released. So I have not gone through it, but they are making some suggestions, important suggestions. So as we go forward, these are the three very important global standards. IEEE 519 I explained to you for both voltage limit and the current limit. IEC 61000-4-30 Class A Edition 3 I explained. What I have probably left out is IEEE 1159 or EN 50160. I have a couple of slides on this. I will cover this also. Not tough for you to follow. If you are interested in this topic, I'm sure I'll be able to give you very easy and simple dosage. These are the limits for IEEE 519 2014 for various parameters. For this is not applicable in our country anyway. From here it starts as per the regulation. From 11 kV to 69 kV is one bandwidth. 69 kV to 161 kV is another bandwidth. Above 161 kV is the third bandwidth. So these are the three bandwidths we are worried about: 11, 22, 33. And then you will find 110. Some people will also have 66, but you will find 110 and 230 kV. These are the various grid levels available in our country for industries. So for the voltage distortion, THD voltage, you will find these are the various values. 5 for 11 kV. If it is total harmonic distortion, it is 5%. Individual order harmonic, that is third or fifth or seventh, we saw that when we talked about basic understanding of harmonics. The third or fifth or seventh individually should be limited to 3%. Total harmonic distortion integration value can be 5%. If it is 110 kV, it will be 1.5 and 2.5. If it is 230 kV, it will be 1 and 1.5. So this is so far as the voltage is concerned. For current, we have two charts. Up to 69 kV. So this is now available from even household appliances. 120 volt is the, or 110 voltage is the voltage level for domestic in the USA. We have 230. So if this standard covers from 120 volt through to 69 kV, then it should cover for domestic also. But this is not implemented for domestic, single phase industry supplies also. It is not implemented. It is 11 kV and above only. So in this chart, you will find 11 kV and above. The limits of for TDD, total demand distortion. This is based on fundamental current. This is based on the average load current for last 12 months. So that is the only difference. The same numerator, denominator alone will change. And this is decided by the ratio of short circuit current to the load current for 12 months. So typically, I find in the Tamil Nadu industries, the ratio of 50 to 100 is applicable. Most of the industries will be required to meet 12% TDD or below. Some will come in 8, some might come in 15. This is the chart for 69 kV and above up to 161 kV. That means 110 kV industries will come here. Same slabs of ISC by IL and TDD. As you notice, they are mostly half of what is it for at this level. So large industries in 110 kV will have to be very careful in understanding that the IEEE 519 2014 has different charts for different voltage levels. Same hospital, same one full day window. Let's look at the harmonics. So when we capture the harmonics, we look at the THD-R value, because this meter which I am using does not measure the TDD, but it's always possible to mathematically derive this THD value to TDD. Now this THD is based on the fundamental current, first order current. If I know what was the last 12 months average current, we'll be able to convert this using an Excel sheet, what is the TDD, and report to the customer. As you can see here, the average for this one full day, the harmonic current, THD, total harmonic distortion, did not reach 8%. At that time, that was the standard. So this hospital was well within the 8%. So we certify saying that this hospital is not polluting the grid. So this is from the same one-day recording. Now I spoke about resonance. If you recollect that graph where the grid impedance and the capacitance, when they resonate, they will create amplification of harmonic. As you can see here, this is the pure sine wave when the capacitor is switched off. APFC panel is switched off. Automatic power factor correction panel. The same thing when it is switched on, you see the distortion in the, this is harmonic. From 3.4, 3.5, 3.8% RYB, it is increasing to 21.5, 23.3 and 22.8. This is primarily because of the resonance that is taking place. Most of the resonance will happen around 11th order. I will show you later on in the same facility how the 11th order harmonic is causing the amplification. So I'm just making a commentary here about amplification caused by harmonic. This is a couple of slides I added today. In fact, last night I shared my slides with Dr. Sanjay Court with the fear that if I have any interruption, at least the slides will be safe in his hands and I can request him to put it up if I'm not able to put it up myself and come in front of you and speak to you. So after discussions with him, after understanding that the audience mostly will be from Maharashtra, I decided to add a couple of slides specifically for Maharashtra based industries and consumers. So the new billing system introduced by MSC DCL now calls for KVEH billing. Now what is KVEH? It's a square root of KWH square plus lagging power factor square, KV reactive power square, and leading power factor square, leading reactive power square. So now you will be paying not only for KWH, you will also paying for the lagging and the leading reactive power which we are injecting. These reactive powers are reactive because we are putting it to the grid. This is what we are putting to the grid. This is what we are actually, this is what we are totally drawing, this is what we are actually utilizing, and these are reactive power put back into the grid, and they want us to pay for this also. So it is not only active energy, it is also the reactive energy which is getting billed. The simple explanation for why KVEH billing is chosen. Now, I have a question. I may be asking this question at the appropriate quarters. If you are paying for all these energies like here, why then should we pay for a fixed contract demand? This question is there in my mind. I'll be asking the appropriate authority. Maybe TNERC or any other ERC, central ERC also. We can write this question, ask them, so that the fixed charges, contract demand charges are removed from the bill, which will be a great relief as you saw yourself. Now, I have a slide here which talks about power factor, evolution of power factor. We all know the relationship between kilowatt, kVA and kVAR. So as you can see here, this vertical is kVAR, reactive power. This is the base in a hypotenuse. Hypotenuse is the kVA. The base is the active power or kilowatt used. Pythagoras theorem. Or in simple words, we can explain this easy for many of you to understand. When we buy or a bartender, when he fills up a beer in a glass, he fills up beer up to this and some froth or foam at the top. None of us will drink this. We drink only the beer. So that is the actual power put to use. This froth is a waste. We sometimes blow it away from the glass. But we are paying for the entire. Now you will understand the concept now. So the relationship actually, as per Pythagoras theorem, the kVA, which is not in phase with this kilowatt, because of the phase angle difference caused by the reactive power, kVA will be square root of P square plus Q square. P square is the active power, as you can see here. Q is the reactive power. So square root of P square plus Q square, or in other words, square root of kilowatt square plus kVAR square is equal to kVA. And the relationship of power factor is kilowatt by kVA. It's a ratio. Now, with the advent of nonlinear loads, KVAH billing, and new understanding, we have to add one more element, not only the active and reactive power, we also have to add distortion power. As you can see in this graph, same Pythagoras theorem, but now you have additional losses. Third element. So that third element is the distortion power. So you have a reactive power caused because of capacitor, distortion power caused because of the harmonic. You saw how harmonic emancipated, no? How it showed up in the network. So that show will also be a penalty for us. So therefore, new power triangle will be kVA or S will be equal to square root of P square plus Q square plus D square. Now, I do not know if Maharashtra is planning to configure the meters for capturing the distortion power. Some meters in Andhra Pradesh, in my experience, did not capture the reaction, did not capture the distortion. So between my meter and the trivector meter of the industry, there was a gap. But in one industry, we were able to capture and show, and I will show that as a case study. There is only one case study, but the idea is for me to explain to you what is the new power triangle and what does it give rise to. Earlier, power factor was kilowatt by kVA. Now, it will be true power factor. That means you will have THD multiplied by TDD. Both will be multiplied and shown. And that is what will be true power factor, as you can see here. Now the true power factor will be 1 divided by square root of 1 plus THD square and square root of 1 plus THD, voltage and current, both will get multiplied for you to arrive at the power factor, which is called as true power factor. This is only displacement power factor. Here it will be true power factor, which is a product of displacement power factor multiplied by distortion power factor. This understanding is important for you to apply as and when you see a power bill. If you are going to find out why the gap is very high, in spite of the fact that the displacement power factor was close to the unity, then you will always attribute that to the distortion power factor, which should have been configured in the meter, trivector meter. So this idea, let it remain with you. Anyone, again I'm repeating, if you want to expand on this understanding and knowledge, very difficult for me to handle it in 1.5 hours. My slides, number of slides expanded close to 70, as you might recall originally. So this is the essential difference. So let's look at the solution concept. Now, if you put a capacitor to fire, you are actually adding fuel to fire. So you cannot have a plain capacitor. So what you should do is you should provide plain capacitor is adding fuel to fire. So now what you do, you are adding a filter or a device in between to prevent that from applying to the fire. So the amplification will not take place. So what you see is a inductor or a resistor in series with a capacitor. Similarly, if you have active harmonic filter, apart from the series inductor, if you add an active harmonic filter, आग भी बुझा सकते हैं. It is possible for you to reduce. Now you are not putting fuel, you are putting water to the fire. So the fire can be put out. No better slide can explain the concept to you than this one slide. मैं तो फिदा हो गया था इस slide के लिए, इसलिए I decided to use this slide for you. It was given by my mentor and guru, almost my M.R. Srinivasan. So we'll go forward. Just give me a minute so that I can charge my laptop. Yes, I'm back on even keel. So, these are some of the solutions for a fixed bank capacitor. Typically, you should use a reactor in series. This is how it will look. So, plain capacitor should be treated like this. A plain capacitor, cylindrical shape. In series, you have an inductor. So, supply cable will come to the reactor, and then it will come to the. It's coming from here. Cable will come from here, go to the reactor. From the reactor, it will come to the capacitor, so that the capacitor and reactor will be in series. So any fixed bank capacitor should be converted like this. Wall mounted also is possible. Or if you have an APFC, you should convert them into detuned APFC, where you will find main incomer, capacitor is behind this, these are the contactors, and the reactors in this. So you will have 3-panel arrangement for APFC, which is what is generally electricity inspectorates permit these days. So this is one suggestion. Few slides on the power quality. I'm trying to take it as simple as possible so that you will appreciate what I'm trying to do. I am not taxing your mind or your brain. Simple thoughts. I'm just leaving them with thoughts. Anyone who wants to expand this, either me or Google University is there. Please take a look. So if you look at the power quality issues, most of the power quality issues will be either power factor, voltage variations, voltage unbalance, some of the equipment loads can be unbalanced, harmonic distortion, under or over voltage, frequency variation, sags and swells, transient and harmonics. These are typically what the power qualities are. Maybe what is missing here is a flicker. I will try and remember to add them the next time. So flicker is also a power quality issue. Now, sags and swells are the most affecting in the power quality. So we will be paying some special attention to sags and swells. So the standard for power quality, apart from IEEE 1159, I also spoke about EN 50160. Most of the meters that you find, whether Cricard or Fluke, are configured to give you reports based on EN 50160. We don't have to break our head. But then for understanding, I have given you some inputs here. So this particular information on voltage, sag and dips is a half cycle value. 10 millisecond is half cycle, 20 millisecond is 1 cycle. So that in 50 seconds, 50 cycles are there in one second. So 10 milliseconds, if you capture the value for 1 year, 100% of the time, the sag should be within this limit. 10 to 100, 1000 times, 85% nominal. It should be under 85% nominal. So it should meet sag, because the sag is actually causing a lot of damages to the production efficiency. A lot of interruptions are caused by the sag. So therefore, again, I'm repeating, voltage, sag and dips are very important for us to understand. And as you can see here, IEEE 1159 also talks about voltage sag for 3 different durations. One is called instantaneous, the other is called momentary, the third is called temporary. From 0.5 cycle to 1 minute is how they have divided this into three categories. Typically, solutions are available after 2 milliseconds. So from the 3rd millisecond to till 30 seconds, not 1 minute, 30 seconds, it is possible to hold the dip in the voltage, or 110, 120% of the swell in the voltage, such that the sensitive electronic equipments will not trip. I have one again a commentary. As you can see here, sag is 56% of the PQ problem, and swell is 31%. So between them, this is about 87% of the problem. The spikes and outages which are happening are easy to understand. So sags and swells are the 2 important loss-making activities. So we have to be very careful about them. So in this case, in the same hospital case, if you remember, in the same 24-hour window, we identified the sag occurring, a dip in voltage, as you can see here, highlighted, or here, 1 half cycle cursor, where I have kept the cursor is showing the voltage available in one phase as against 10.6 kV. It's 11 kV supply, if you remember, HT side measurement. The voltage has dropped to 6.44 kV. That's a substantial, substantial drop in voltage, which can cause interruption to electronic equipments. Generally, sensitive electronics, including VFDs, can read this very quickly and fold. They will disconnect the supply. looking at it as a danger to the equipment. So to protect the equipment, they will fold. And that is when you will find that the equipment has stopped. You will wonder why it has stopped. You will go and then you will again check everything. If nothing is wrong, then you will switch on. It will start running, because by then the voltage is restored. So this is what we have to understand. So this is from the same slide. I'm sure you will appreciate that I have not taken you to too many slides, too many sites. In one site, we have identified so many activities, and then we were able to, in one window of 24 hours, discuss various parameters. The same thing, another method of looking at this is focused. It has happened at 8:34:28 on that day. This has happened, and this is what is the drop in voltage. Against this is the amount of drop in voltage, and the equipment, one of the equipment tripped, and then we asked them. This is hindsight, right? We asked them, did anything happen? And they recollected, yes, in the logbook, somebody has written that there was a trip of some window ACs with inverters. So window ACs with inverters will definitely trip whenever they encounter such a dip in voltage. So it's important for us to understand this. Solutions available. UPS is a good solution, which is very popular. Most of you will be recommending this. Dynamic voltage restorer is a new solution, which most of you may be newly hearing. Ferro resonance transformer is also a new solution. I think I have a slide which talks about. I think I wanted to add it. I didn't add it. Sorry. DVR is the best choice. Very expensive, but it will be. If you look at the total losses you have in the system, it will only be 0.5% of the cost of investment you will be making for solving this PQ problem, this voltage sag as well. So anyone interested can discuss about it. UPS is a very popular choice, but UPS online particularly has a poor efficiency. It has a, the batteries and the AMC. AMC is almost 10 to 20% of the cost of the equipment year on year. So all these are prohibitively expensive. You will find that the DVR can do the solution, maintain the power supply adequately, and still be less than 25% of the losses of the UPS. So new idea maybe, I want you to think on it, develop your understanding and go forward. So I have one success story. Allow me to have a sip of water. My voice is failing. So this is an FMCG manufacturer in Andhra Pradesh where there is kVH billing. What we did, this is the solution topography or solution architecture. They had a point of common coupling 33 kV incomer, 2 transformers, and then the main panel. This was the 433 volt bus. It was going to 10 workstations or MCCs, motor control centers, 10 numbers in the shop floor. And they had 4 chillers. They had a DG set and a compressor also, common header. The harmonic level, when I showed you, you'll understand, was very high. As you can see here, the harmonic was 19% average, 24-28% maximum. This is again a full day window, if I'm not mistaken. Yeah, 10 to 2016 to 11 to 2016. It's a 24-hour window, and we measured this value. The maximum was 28%. The average was approximately 19.4% or 19%. This is definitely not acceptable. But in Andhra, they had kVH billing. This is bordering Chennai, Sri City, Andhra Pradesh. So what we did was we told the customer that this has to be brought down. And we also wanted to tell the customer what is the impact of this. So after we did the surveys, you saw this slide, we provided for each MCC 60 ampere active harmonic filter. This facility already had a detuned APFC. So we did not look at the amplification as a problem. There was no amplification, but the harmonic content was very high in each of these equipments. Chinese equipments and heavy harmonic was there, and they were also affecting parallel branch circuits. And they had huge failures of PCB boards. They were spending almost 1 crore for PCB boards replacement or repair or whatever. That was the kind of situation in which they invited us, and we found that the harmonic is causing the problem. Harmonic is not getting amplified because any amplified harmonic will flow towards the grid. That was not the problem. So then we designed active harmonic filters for 10 of the MCCs, one each 60 ampere for the chillers, because these are also 6 drives. And then overall 2 numbers of 300 ampere active harmonic filters. This was required, warranted, without which we would not have been able to bring this kind of result. From something like 19%, we brought it down to less than 4%. So once we achieved this, we wanted to educate the customer as to what is the cost benefit. I have written this particular case as case study number 49 under APQI, Asia Power Quality Initiative, in which I am a member. Reduction in kVAH billing through harmonic mitigation. So I've just taken, I could have used the same 24-hour window to show you what is the kVAH, but then I thought I will quickly come to the conclusion of this. So this was in one time when we did the audit, was 18.7, 17.1 and 17.2 current harmonic, brought down to 3.7, 3.2 and 3.6. The difference between kVAH and kWH was 610 with this kind of harmonic. It was brought down to 150. So the per day saving was 460 units. Per month saving was 13,800 units. And the annual extrapolated saving was 1,65,600 units. So at that time in 2016, the tariff was 6 rupee 32 paisa, and the client saved 10,46,000 rupees per annum because of the provision of harmonic filters. But what is important is, I have spoken to them even recently. I made the same case presentation to another college in Pune. That time I decided to call them and speak with them to find out what was the net effect of what we did 5 years back. They told me that the board failure has come down to below 3%. Board failures are there, but then it is very, very close to zero, below 3%. And he says, although it was 70 lakhs worth of investment, 7 years would have been a typical payback based on a fixed cost of 6 rupee 32 paisa. But he says, I have already earned that investment in the first year itself, because I was paying almost close to 1 crore for restoring all the PCB boards. So this is the kind of results we were able to bring. So I am trying to convince you that harmonic management is important for kVAH billing, both in terms of bringing down the power factor, bringing up the power factor close to unity, and bringing down the harmonic distortion levels. I think a couple of slides, just be with me, I'm completing. This is a technology pyramid based on the cost. So typically 7% detuned filters will be the first level of investment, or if it's a third order harmonic like IT parks and corporate banks and things like that, 14% detuned filters will be the solution. Tuned filters is again a solution available in terms of cost, costlier than these two, and still costlier will be hybrid. And then the best in class is the active filters. And today we have other technologies like active front end, and so on and so forth. So a typical cost pyramid will look like this. That was my last slide. Thank you very much. I don't know whether I was able to keep you riveted on this presentation. Did this make any impact on you? This is my mobile number, my mail ID, and I write my articles, small case studies on LinkedIn in the name of Srinivasan Jairam. Jairam is my father's name. Srinivasan is the given name to me. My request would be to connect with me, read some of my articles, ask me questions. Quickest connection would be a mobile connection, but then if you find that I am not answering your calls, I'll be obviously sitting in front of the system conducting some webinar or so. So I would have missed most of the calls which came to me today in the last 1.5 hours time. What is the time, sir? 15:53. So I don't know if I finished it within time. I may have taken slightly extra time. Forgive me for that. I'm a stickler to time. We didn't start at 2. We started around 2:15, if I'm not mistaken.
Yeah.
So I think this is 1.5 hours approximately. So unless you want to hold me to question answer, we can conclude and you can go happily. Thank you. Thank you very much, sir.
Is there any question you can ask in chat box, or you can ask directly by unmuting yourself?
And you have started with that basic, that was expected. Actually, it was essential for all the participants. You have very nicely that started that harmonics, that basic things, and brought to up to still that installation
Case study.
of different types of filters and cost benefits also you shown very nicely. It is actually. That means that harmonics, even it will affect on the consumption also. Consumption, so many things are there for harmonics.
Yes, yes. In Tamil Nadu, it is penalty.
Okay.
Many people have been forced to take the action. But wherever it is KVAH billing,
Yeah.
if the effect of harmonic distortion is not included, I would imagine people will continue to do business as usual. But if it is also included in the trivector meter, we will have to be very careful about managing the KVAH billing.
In Maharashtra only that KVH billing is for the HT consumers, and even that harmonics is not included. For LT still it is KWH, it is for LT, all the LT, but there the power factor is there, no harmonics is there. But for HT it is KVH billing. That means indirectly the power factor.
They won't tell you to reduce the KVH if the gap is high. They will happily take the payment from you. So in our own interest, we'll have to do this exercise of reducing.
Great, great.
So I don't know how many people really stayed back, but I hope people will not feel sleepy enough to keep quiet. You can unmute, ask questions. I'll be happy to explain. Or if you think I have not given any room for questions, I would happily fold up. You can write to me for additional information and knowledge. I'll be happy to provide.
That would be better.